real right in this case. Which symmetry is compatible with real right? Okay, so yes, yeah, let me finish first. Okay. So what? Yeah, next I go to another topic, symmetry. So shall we? Break.
So in the second part, you will have perhaps 1 hour, and it's enough to finish your lecture.
I'm not sure.
Maybe you can, because you have 60 pages left. I'm not sure.
Yeah, many technical part I will skip. So yeah, okay. So then let me start this section for a few slides. Okay, so the symmetry. Okay, so what kind of symmetry exists in non-Hermitian systems? So in this talk, I didn't fix, I didn't mention physical systems. So that means I cannot determine what symmetry really exists in Hamilton matrix. However, we can consider mathematically. I mean, some symmetry type which has a good structure mathematically. Okay, this is my logic, my strategy. Okay, but sometimes okay. So before introducing the classification of symmetry, let me show some example symmetry which maybe are relevant. Okay. So the first example is time ratio symmetry. Yeah, like this. You know the time ratio symmetry should be important. Okay. The other symmetry is particle Hall symmetry. So in the near field approach to the superconductor, you use the Pogolyov Hamiltonian HBDG, and this Hamiltonian intrinsically has particle Hall symmetry like this. So the BG Hamiltonian has diagonal part I have with normal part, and off diagonal part the function part no I have. The point is because of fermion anti-commutation relation, this gap function is scale symmetry. Then that means this Hamiltonian, BGG Hamiltonian obeys this type of symmetry. So transpose symmetry. Okay. And of course, if the Hamiltonian is early, this is equivalent to the complex conjugate. But we can say that this type of symmetry is also particle symmetry. Okay. Another example is bosonic BGG Hamiltonian. Let's consider bosonic quadratic system. It is given by a quadratic Hamiltonian HBDG. But in bosonic system, we have to diagonalize this Hamiltonian by with keeping the bosonic commutation relation. That means we have to diagonalize this Hamiltonian by using parallel unitary matrix. Yeah. Then we find that this is equivalent to the usual diagonalization by using unitary matrix of another Hamiltonian. This one sigma z h BDC. Okay. Then so then this Hamiltonian is non-Hermitian, non-Hermitian. Even if there are HBDGs, no Hermitian. However, because this original Hamiltonian is Hermit, this non-Hermitian Hamiltonian has should Hermit. So this is an example of Dagger symmetry. Okay, so I introduced complex conjugate and transpose and Dagger. Okay, so I think these are natural symmetry constraints in non-Hermitian systems. So in this talk, let me restrict my concern of symmetry in the following 8 types. So yeah, first of all, the symmetry is given is characterized by some unitary matrix U, and we take the conjugation by U. I mean U and U dagger from left and right, and also I can choose 4 types of transformation of matrix H. H itself and star and transpose and dagger. Okay, and also in the right hand side I have 2 signs, plus and minus sign. Okay, so in this talk, today's talk, I consider this type of symmetry constraint on non-Hermitian matrices. Okay.
8 is 4 times 2.
It is
8. 8 is from 4 times 2. Is that right?
4 times 2.
So 8 times
Yes, of course, yes. 4 times 2.
Yes. We know the symmetry acting on complex conjugation and also transpose. I assume you have no degrees of freedom to change dagger. All right? I mean, I don't think the 4 is in.
You mean with your constraint a situation where the symmetry, where the 2 symmetries, one is a star and one is dagger.
Whatever. 2 out of 3. If I know 2 out of 3.
The dagger symmetry is the symmetry that he defined previously, which is something related to the right function. The dagger symmetry is not complex conjugate and transpose, right? Here.
Dagger symmetry is just the usual dagger.
Because if it is the usual dagger, then
conjugate.
if it is the usual dagger, then you can get it by complex conjugate and transpose.
Yes,
that's the question.
Oh, I see.
It's not 8.
I see. Okay. Yeah, the same. Yeah. I mean the product of dagger means
Composition of complex
combination of
3 are independent.
no. I mean
They're
4 are
separate.
independent.
What?
They're separate. I think they are 8 separate types. So you don't combine 2 together.
What you see on dagger is complex conjugation.
No, okay. So so that I mean if I have 8 star symmetry only, then I have transpose symmetry. I have no transpose symmetry. If I have transpose symmetry only, I don't have star symmetry. So
Okay.
I think I got it. Thanks.
Okay, so yeah, let me
Stop here. Yeah. Okay, so now we are taking more questions. It's supposed to be 15 minutes for this in-depth discussion.
Okay.
So you will start in the next section about this with the theorem, or
the original
I mean, in the previous slides you haven't finished it yet, actually. The second point is about the weakness theorem. Are you going to discuss about that?
No.
Yeah.
No. No, you're not going to discuss it.
Okay.
So this is just a remark. So in the Hermitian system, in quantum mechanical system, we have guiding principle because the symmetry is defined as a transformation of observer, which does not change the progression function and the physical quantity. And but from this definition, we can prove that that symmetry can be represented as a unitary or anti-unitary transformation acting on Hilbert space.
Yes.
Okay. So this is a case of quantum mechanical system. But here I didn't mention about the physical system. So I have no guiding principle.
I see.
So this is just one point. And another point is we can extend this symmetry in the following way. So here I use the same U. Then we fix U. So we can consider the different matrix U and V there. And also we may consider arbitrary phase here. Right. My point is we can easily extend the definition by hand.
Yeah, but why choose this extension? That's not obvious to me, right? So it's just based on the mathematical multiplication.
Yeah.
Not based on
Yeah. But it turns out that this type of symmetry, U and V together, with sign plus minus, is useful to detect some non-Hermitian topology. Yeah, sometimes mathematically it is very useful. We can but it's not originated from the physical system.
Any questions? I encourage students and postdocs to ask, especially for a student, maybe.
Yes.
Those curve, and is this always true?
You mean the question is PVC spectrum is a closed loop, and if this is also always true.
And
I think true because in the PVC the is defined for copper. And its spectrum is also periodic.
so you gave one example that if there's no spin effect, then just open up.
In this one,
Yeah.
even in this case, this is copper.
But it's not closed.
Closed, closed. Yeah, this is circle. From this is the starting point. Let's say this is starting point, and the trajectory is like this.
It's a closed curve that collapses.
Oh,
Yeah.
going back.
Yeah. Yes.
Oh, what is the point is short. The line point gap or line gap.
It's like edge state in Hermitian system. So yeah, okay. So let me show simple example. It's called linear model. Let's consider one-dimensional lattice, which are there are 2 degrees of freedom on each side. And let's consider this kind of opening model. And let's consider this open boundary function. Then this degree of freedom is free. So the energy, this energy is 0. Okay. However, in the bar, I have this hopping term. Then this hopping term, I have the bar energy E equal to plus minus T. This is an example of edge state.
So this point and this will affect the expectation of if we want to do the application of this symmetry, there's the point at the center of that. Is there this point will reflect something?
I don't think the point, the existence of the point will break anything. It's just an edge state.
This one. And this is the winding number for one-dimensional system. Yeah, it's KX. By not over 1 x
Can we follow up that question? So in principle, if we want to generalize it to higher dimension, what will happen?
Yeah, generalize higher dimension. So depending on dimension, the classification becomes changed. And depending on dimension and symmetry and the gap condition, I mean point gap or line gap, the classification is going to change. Then that means the topological number is also changed.
So is it well studied yet, or it is very?
Very studied, yeah. Yeah, I think all. Yeah, yeah. So eventually, the topological invariant is discussed as a topological invariant in Hermitian system. I think topological invariant is already known, but the physical phenomena related to this the topological invariant are I'm not sure already known yet.
But if it is in high dimension, then it's kind of hard for me to understand what we mean by integration along K, like which direction I should do. Yeah, like
So,
I think
for example, you can imagine that you have a hole here, sphere.
I see. So you are saying those winding number are completely decoupled. I just do, one winding number in X direction and one winding number in.
Yeah, you can, yeah.
Okay.
Yeah, okay.
Okay. Then I'm not I'm not sure.
No, I think in two-dimension you have to calculate the 2D winding number instead of just.
I'm not sure the winding number is this, but by Rakchan number,
Yeah. I mean, in Hermitian case, I understand that you can easily generalize it.
Yeah.
But in the non-Hermitian case, because the definition of gap is kind of geometrically related, so I'm not sure how to generalize that in high dimension case. So
yeah, but it just I mean,
so I just
not
just take that formula and do it in x, y, z direction, something like that. If I want to generalize it to 3D.
yeah. It's a kind of weak invariant. Yeah, but the difficult point is the super difficult point is in the Non-Hermitian system, you have to use local Hamiltonian in open boundary condition. That so it's a very subtle point. That's important point.
Can you make the statement again? I didn't.
So there's no one-to-one correspondence between topological number defined in periodic boundary condition and edge state phenomena in open boundary condition in non-Hermitian system. In Hermitian system, we can apply the topological number defined in the block Hamiltonian in periodic boundary condition to detect edge state phenomena in open boundary condition. However, in non-Hermitian system, because of non-Hermitian ski effect, we have to use bulk OBC spectrum, bulk OBC block Hamiltonian to detect quantitatively detect edge state. It's super difficult problem. Yeah. So that I don't explain in the detail in this lecture, but it's super important.
Okay, so I think we should have a break here. We don't have a 15 minutes break. So the next lecture will begin at 3:30.
你可以说你的Hamiltonian其实你不同的比方说方式就是你的能力是变对，
没有就是拍的。正常大概是1、2、2、3，
就是最角落的 metric element。
对，就是有加了一下。
外的特征。
但是就是他很在意 metric， 没有看加那个嘛。但是他告诉你是如果你用一样的话，可以他就把这个有的时候就会有所谓的正负。
我正中午才换一个满电的电池，我不知道，大概才做得到。没办法，那个麦克风我自己。
对，您签一个名字。然后像今天晚上，所以你们要领队带他们去吃饭。然后那我就想说，对，定6到8位再去让餐厅，就是你说的那个格拉6点。我觉得他也是。好，那这样的话，就是他是说早餐3到7万。你们大概一个400-500块，然后您帮我，对，但是。对啊，可是就是他们就说国际性会议好像不好要，对，一定要有外宾。那您是说您报在您那边的计划，比如说可以把没有，因为我现在的想法还是给我报，然后你想办法。没有，我就想办法把它塞到这个还是想办法，就想要搬到晚餐的餐点。然后那这样的话，就可以就是大家不要凑人数，所以不要吃太贵，然后大概我个人在1000名之内的8这样子结束。对，然后我先给老师，可是现在比较麻烦，因为你在北大。我现在先给你一些鸡蛋去，然后看在对手，然后因为可以请一样帮我们打一下，就变成只能说如果是报的话，我们就打，对啊。或者是即使报很低的，只要处方报就是但是没有，我应该还是交代一个小配款。我在想办法。没有，我在想一下。那就我先给你填。第一个签还是你就不要把这些不是，那您再把没有，您再8000之后。 拿铁出来，然后再今天再会有。不是啊，每个人也是规定第一天200，第2天300。反正我就要想办法把它，反正我会想办法。就是我们要想别的名字都贴给做到吧，我觉得不确定吧。但是老师有听过吗？老师有听过吗？
第二个是，因为我中午换电池，我没考虑到现在差几点。我发，我觉得第二3分钱。我是导师他出门，他开了2场。
Yeah. So this is
开头百万一种。So I mean, presentation of what is
An hour for a lecture.
Because this time
later. And the side is
randomly choose the in the previous slide, last time skin. 那就是。
老师晚上要算吗？
So in the system,
大概差不多吧，很有创意的，差不多。
给他们一个安心的借口。
So it's a point spectrum with H state and state effects.
饭店吗？我去服务饭店。知道，昨天有，昨天是跟中研院
All right, so we'll start the second part.
Hey, Rich, let's continue our. So, yeah, I introduced 8 types of symmetries in the Non-Hermitian system. The first one is H itself, complex conjugate, transpose, dagger, and also the right hand side I have plus or minus sign. Okay. Okay, then the question is, what kind of how many types of symmetry this construct? Yeah, let me explain the detail. Okay, so before the classification of symmetry, let me show some generic definition of symmetry. Okay, so suppose Z is a symmetry group like Z2 or G4 or G2 times D2. So for each element of symmetry group Z, we introduce some homomorphism phi, eta, C that specify this symmetry group element small z is which type? So eight types of symmetry I previously introduced. This one. Okay, so phi means this symmetry is complex conjugation. Okay, and eta means that this symmetry includes dagger, Hermitian conjugate. Okay. Then, for example, if phi and eta, both phi and eta are negative, then the symmetry is a type of transpose. Okay. Then also I have C, homomorphism C. It's a sign. It appears at the right hand side of the symmetry constant. Okay. By the way, the homomorphism is just yeah, the function which without the group structure. Okay.
Excuse me, is there a typo in the phi and theta?
Typo phi and theta. Which one?
Yeah, for example, you say phi is -1 if there's a complex conjugation, then
Yes.
the third one should be plus, right? Because then
Yeah, it's not typo. Not a typo. So my definition is if there is phi, I have a complex conjugation.
yeah,
In addition to phi, if I have eta, if eta is -1, then in addition to star, I have dagger. This is my definition. Okay.
okay.
And also because this is a symmetry group, this symmetry should, I mean this matrix UZ should obey some consistency condition from the group structure. Then actually we can show that you comparing the consecutive successive transformation by H and G and this one transformation by G times H, we have this construct. I mean UG times UH. If by G is 1, I mean there's no complex conjugate, then UG times UH should proportional to be proportional to UGH up to U1. And on the other hand, if phi g is -1, then we should have conjugate here. Then this combination UG UH star should be proportional to UGH up to U1. And also I have some consistency conditions from associated experiments. Okay, so actually, so let's give a name of H type of symmetry. So this is just a name of symmetry, so it's not important, but it's useful for if you are familiar with some name of symmetry. Okay. So the first one is just usually unitary symmetry. So the second one is a Dagger symmetry without minus sign here. It's usually called pseudo-Hermit system. And yeah, tensor symmetry is star symmetry without negative sign. Yeah. And this one, time reversal Dagger symmetry, this is a kind of new symmetry. Sorry, this is a kind of new name of the symmetry in Non-Hermitian system. It is a symmetry type over transport without negative sign. And also I have particle symmetry. It is defined as transport with negative sign, and particle hold Dagger symmetry because if I have Dagger, in addition to transport, I give additional Dagger, so I have star symmetry. So this is called particle Dagger. And also I have some sublattice symmetry, which means the Hamiltonian is anti-commute with some intermediates. This is called sublattice symmetry. And finally, I have chiral symmetry, which is defined as a Dagger symmetry with negative sign. So, but this is just a name of symmetry. Okay, so the question is, how many fundamental different symmetry class there are? So the answer is first. So we eventually get distinct 38 symmetry class in Non-Hermitian systems. So this can be constructed with tenfold away, tenfold around single symmetry class in Hermitian systems. So my point is, in non-Hermitian system, with some definition of fundamental symmetry, we eventually get 38 symmetry classes. So let me show our logic. So the first step is that if the Hamiltonian has a unitary symmetry is this one, this. So the Hamiltonian is commute with some unitary matrix of the group element. Then, as a matter of mathematical fact, if there is such kind of symmetry, the Hamiltonian is block diagonalized with respect to irreducible representation of such a unitary symmetry. Okay. So so for each irreducible block, the other symmetries which is not unitary act as a D2 symmetry. Okay? Because you can see that this, except for unitary symmetry, unitary symmetry, if we consider this type of symmetry twice, we get the unitary symmetry. Right? So that means on top of irreducible block, the other symmetry, it is not unitary, behaves as D2 symmetry. Yeah, this is mathematically justified by it's called the William criterion. Okay. So then we can see that we can conclude that there are two patterns. The first pattern is the other symmetry, which is not unitary, preserves the irreducible block alpha, and also that means that this group element G is closed inside this irreducible block. Okay. So this is actually a true G2 symmetry inside this block alpha. Another pattern is G exchange the irreducible representation. For example, alpha and beta. In this case, effectively, the symmetry G disappears. Okay. Because H if this is the case, the Hamiltonian H beta can be is just a copy of H alpha by using group element small z. Okay. So that means the second pattern we can neglect. We can forget the second pattern in the classification. Okay. Okay. Yes.
So can you remind me 5G, theta, G, and CG? What are the symmetries that stands for them? What are the symmetries for these three categories? One is time reversal, and the other is dagger, and the last one is the particle hole.
The transpose. You mean in Hermitian system?
No, I think.
Oh, in here, yeah. So GABA and the star and transpose, and also minus R.
So I want to ask the question because I think Wigner's theorem tells us that.
What Wigner's theorem?
Yeah, in the Hermitian case, you can prove that for symmetry there are only two types. One is the unitary, and the other is the anti-unitary. And the relevant anti-unitary are the C, P, and T. But in this case, are there things like that you can have similar proof that this is not also relevant?
No. It's because I didn't mention
realization.
Yeah.
I see. So this is just chosen by hand.
Yes. And this is just a mathematical fact of representation.
Okay.
So the property, for example, the phi, eta, and c could be different for different block. Is that correct?
different growth. I don't understand.
For example, I have a block, H alpha and different block,
Growth. I mean,
H gamma,
okay.
and they are not related. And can they have different value of phi, eta, and c? Or it must be the same for the whole system?
Same. Because phi and eta and c as a property of group element.
For the whole system.
For the whole system, yes. Okay, so what I said is we can forget, we can focus only on the one reducible block, and the second point is we can forget the symmetry that exchange different blocks, reducible blocks. Okay. Okay, so yeah, the third point is that I said just as. So the problem is because that how different symmetry actions there are in a single block HR. And also because we can assume the absence of unitary symmetry, the group symmetry group can be the absence of unitary symmetry is the strong constraint on the possible symmetry group G acting on the one reduced block H alpha. I mean, G is either trivial or D2 square and D2 cube and D2 fourth. Sorry, sorry. Okay. Otherwise, there is in other case, there should be one unitary symmetry element. Okay, so then the question, so the problem is very because the finite problem. Okay, so that we can classify very easily. Okay, so let's start. So before the classification, I have one remark. For the group element Z with this is a typo. Sorry. For group element G with negative phi. Okay. Then anti-unitary symmetry. H square is proportional to IHT. As a group element, this square is identity, but its representation is not identity. Okay, in general. So in general, for group element which is anti-unitary and which is G2, then such square in the representation is either +1 or -1, which you can prove. If you are interested in the group, you can read this. Okay. Okay, so yeah, let's start the classification. The first case, the trivial case, of course, is unique, no classification. However, okay, so yeah, so let's consider the case where the symmetry group is D2. So one generator exists. I have 7 patterns. This is a pattern of phi and eta and c. So because this is a complex conjugation, and this is dagger, and the negative sign, c is negative sign in the right hand side of symmetry constraint. I have 7 patterns here because I have except for each 7 pattern corresponding to this 7 pattern. Okay. Okay, so and also if the group this generator is anti-unitary, I mean phi 1 is -1, we have two choices. Wait, before this one. So eventually I get 2, 2, 2, 2, 1, 1, 1. So 11 classification in this case. Okay. Okay, let's consider the second, third one. The group is G2 squared. Then the case where the anti-unitary group element is included, there are 4 patterns. This one, and this one, and this one. Okay. And each choices, we have two by 2 choices. I mean the U1 square and U2 square for each. So then eventually I have 4 and 4 and 4 and 4. If the anti-unitary group element is included. And also, okay, so this is the case where anti-unitary group element is included. And the case where there's no anti-unitary group element, I have just one pattern. 1, -1, 1, and 1, 1, -1. Okay. And in this case, there's 2 patterns, 2 choices. It just comes from the anti-commutation relation between U1 and U2. You can find that the phase is stayed under the change of the phase of representation. As a result, I have 4, 4, 4, 4 plus 2, then 18. Okay, this is our last case. The group is G2 third, sorry, G2 cube. Then in this case, there should be one anti-unitary group element. Okay. Then, yeah, other result, yeah, the pattern is unique. We can choose this group element as a generator of D2 cube. Then for each generator, I have two choices of U1 square and U2 square, U3 square. Eventually, I have 2 times 2 times 2 times is equal to 8. So I get 38 defined symmetry classes. Okay.
Question.
Yes. You mean this one?
Yes.
No, different. So independent.
Can we have, for example, if n equals 3 here, can we have phi1 equals +1 and phi2 equals -1? Something like that.
I mean, minus a plus 1, minus 1?
Yes.
Yeah, that the point is, we can always choose these 3 as a generators for this symmetry form. Yeah. Okay, so this is end of proof of the classification of symmetry classes in Non-Hermitian systems. Okay. This is a side remark. So, yeah, in the pioneers work by Bernard and Nuclear in almost 20 years back, they constructed, they discussed 43-fold process in non-Hermitian matrix and discussed the property as a random matrix and Dirac Hamiltonian. And yeah, there's a discrepancy between 43 and 38. But this is due to in our paper we find that they overlooked some overcounting of some symmetry classes and also there's an overlooking. Yeah, so yeah, eventually 38. Our conclusion is that there are 38 symmetry classes in the system.
Yes, in the whole paper, they also consider the same symmetry, but their counting is wrong, something like that.
What symmetry?
I mean, the same symmetry or not? Not supersymmetry. I mean, in their paper, did they consider the same symmetry as in your case?
I think so, yeah.
I see. So they just have to do the math wrong.
But yeah, but yeah, so yeah, your question is that definition of problem is the same one.
Yeah, is it
Yeah,
the same?
yeah. I think it's slightly different.
But the symmetry is the same. Maybe the definition is a little bit different.
But yeah, the overlooking there. So overlooking. I mean, there's no there is some symmetry class which is not discontinuous.
Oh, I see. Okay, so there
Yeah.
are several mistakes.
Yeah, but yeah, but yeah, so yeah, I'm not sure that the division problem is exactly the same one. So
I see.
If we apply our classification scheme to their so, yeah, and we find that some different.
I see. I asked this question because I'm curious about their motivation, about how they choose the symmetry generator. Is it related to some? You mentioned some part about the random matrix theory, so I'm curious. Is it related to some of the nuclear physics or something? So
It's interesting. Yeah. Any application to this one?
Yeah.
I think it's actually ongoing project in some certain organizations. Yeah. So yeah, this is actually some issues that I consider when I preparing this slide. So okay, so we got the classification of fundamental internal symmetry in Non-Hermitian system. So then there, yeah, very interesting programs include under the localization program, because it is originally discussed by Adam Wilson paper in one-dimensional Non-Hermitian system without symmetry. So in one-dimensional system, in Non-Hermitian system, that the localization, other localization occurs. Yeah. Just like discussed. And also, yeah, specular statics. I mean, yeah, random matrix, the property random matrix. It should be interesting. And yeah, topological classification, which I explain later. And also symmetry project exception point. Is there any symmetry project exception point? I mean, it's kind of generalization with exception point using symmetry. And also non-Hermitian scheme. Okay, they exist. So the question is, if we impose, so we have the problem with non-Hermitian scheme effect for 38 symmetry classes, and we can check, for example, numerical, the existence of absence of non-Hermitian scheme, and also the connection to the many body physics, for example. Yeah, you said so. We can apply random matrix theory to, for example, Indo-Brachia spectrum. And yeah, because I didn't mention, but of course we have to apply this kind of mathematical theory to the experimental relevant set. Okay, so so this reference is very limited in my limited because my lack of my knowledge. Actually, currently I don't study the Non-Hermitian physics. So 3 or 4 years back, I studied Non-Hermitian physics, but so I am familiar with the recent development. So I'm sorry that I can't complete the reference. But yeah, I think that some of the problems are not solved yet, and it is currently ongoing project. Okay, and I have to comment on how internal 38 symmetry is implemented in finite dimensional infinite systems. Okay, because I didn't mention the physical system. I have to define the symmetry constraint on the lattice system. Okay. So let me just fix the definition by hand. Okay, so my definition, today's definition is the following. The complex conjugation is local. Okay, so this does not change the spatial position. And on the other hand, transpose exchange transpose symmetry exchange the spatial positions x and x prime by usual transpose is a matrix. Okay, and also Dagger symmetry. Yeah, in the same way, the Dagger symmetry exchange the spatial position. So this is a summary of symmetry implementation of non-Hermitian symmetry. Sorry, this is typo. So I have so unitary symmetry. I don't know the position is not changed. And for complex conjugate symmetry, the position is also not changed. And transpose and Dagger symmetry, the position is changed. Okay. In the momentum space, this is summarized. So in unitary and Dagger symmetry, K is not changed. Wave number is not changed, but star and transpose symmetry K is reflected. Okay. Okay, so I'm not sure this definition is transpose and Dagger. The definition of transpose Dagger is experimentally reasonable, but yeah, mathematically it was found that this is very useful definition. Okay.
If I have a half-pin Hamiltonian, it seems like it is very reasonable, right?
I think so. Yeah. The transpose is
yeah, like change the half-pin orientation. Yeah. I see. So in that sense, because your complex conjugate is defined in this way, does that mean like I'm confused about Hamiltonian, the relation between Hamiltonian and state? So this symmetry is completely applied on the Hamiltonian, but not asking how the state is transformed, right?
Yeah, so transpose relates right eigenmode and left eigenmode. So in this sense, transpose up to state.
Yeah, the reason I ask that is because if you have spin one tap or spin one, the time reversal acts very differently on the state.
Yes.
Yeah, so but in this case, you just focus on the Hamiltonian and not the system.
I see. Yeah. Yeah. In transpose case, we have the same Fermat's linear system.
Yes.
This symmetry, then here's this is right eigenstate with algebra E. Then this. Okay. And taking like this. And this is So that means this is our left eigenstate is the same eigenvalue. And also is orthogonal to each other indices. So that means from here, I mean Hamiltonian is is expanded in this way. So this is from my call. Yeah. So yeah. And the point is yeah probability first in transpose symmetry. But the point another point is in non-Hermitian physics system. Symmetry is the relation between E and Easter. So the conjugate symmetry does not give us the cross generation, but transpose symmetry. So this is a side element. Yeah. Okay, so yeah, I think yeah you are tired. So let me show some demonstration of this program. So the existence of an absence of non-Hermitian sequence for 30 symmetry classes question systems by using mathematical. So the mathematical model I updated in the I wrote it in the summer school box website. You can see the demonstration of writing the spectrum. Yeah, for example, this is a one-dimensional system with no symmetry. I draw the periodic boundary constant spectra and the scheme. And for shared hermiticity test, I also have a scheme. But with subrotic symmetry, I have. With spiral symmetry, yeah, I have. And for transversal symmetry, whose square is 1, and there's a scheme. And transversal symmetry with Kramers scheme. And here, this is a A1 Jaga symmetry. It's a symmetry type. Sorry, it's a transpose symmetry. Then numerically we find that there's no symmetry. There's a discrepancy between open boundary spectrum and closed boundary spectrum. And yeah, and this is another type of transpose symmetry. So this is if we replace the type of transpose symmetry, the existence and absence of skin effects are different. Okay. So I mean, if we consider this ordinary transpose symmetry, I have no skin effect. If you consider kind of symmetry, transpose symmetry with ground degeneracy, I have skin effect. Okay. And yeah, you can check the for 38 symmetry first. Okay. Let me move up the slide. So okay, so eventually we find that the PVC and periodic boundary condition and open boundary condition spectra are the same if and only if the plus A1 data symmetry. I mean, just a transpose type symmetry. Okay. And yeah, that is yes, and this is just a numerical only limited to the numerical observation, but it can be proved mathematically.
What is the typical size of your matrices?
What?
What is the typical size?
System size is 100. And
times 100.
100, yeah, and also internal degrees of freedom, the number of internal degrees of freedom is 4 in this example. So 400 times 400.
So that means there are 4 bands because the internal degree of freedom is 4. So I suppose you have 4 bands.
Bands. Sorry, I don't understand. For what?
When you have internal degree of freedom 4, do you mean you in a unit cell you have 4 stuff?
It's the same as yeah. You can consider internal degree freedom as the different side in the unit cell. Partially, yes. Yes. Yeah, so I see. So if the winding number is non-zero, then you should have skin effect. But even if there okay, so this is example. The plus H dagger, yes. And with this symmetry, we can prove that the winding number is 0 with this symmetry. However, I have a skin effect. Yeah, there's a G2 number. Yeah, defined by this H dagger symmetry. Yeah. Okay, so this is the numerical demonstration. Yeah. Okay, so let me move on to the topological classification. Okay. Okay, so I think probably you may see this periodic channel in the non-Hermitian Hermitian phases. So yeah, so this is a classification table of Hermitian topological phases. Okay, so the A3, A1, B1, this one specify the type of symmetry. So yes, the different symmetry classes. and it is characterized by this T and C and S. And here, delta 0, 1, 2, 3 is a spatial dimension. So that means given symmetry class and spatial dimension, I have classification. For example, class A means no symmetry, and in okay, so class A and two spatial dimension, I have Z. So it is nothing that the existence of a Chan number, and it, yeah, introduced by Okasan this morning. But this is that one example. There are similar to the derivation of 38 distinct symmetry classes. In Hermitian case, we have 10 distinct symmetry classes, and depending on these symmetry classes, and also depending on the spatial dimension, I have the classification, topological classification. If the topological classification is Z, they have Z topological number, and also related to H phenomena, boundary phenomena. And if the classification is 0, there's no such interesting topological phase. Okay, so what the reason I showed this table is that the classification of non-Hermitian topological phases is eventually discussed as the classification of Hermitian systems. So, yeah, let me explain. Okay, so the motivation is we want to classify this kind of interesting topological phases in non-Hermitian systems. For example, as I introduced explained before, skin effect is originated from some topological number with respect to the point gap. In this case, here. The question is, can we classify this kind of interesting topological number exists or not, depending on, systematically. For all 38 symmetry classes and for any spatial dimension. But in this program, the classification of point gap to topological phases. But this problem is easily solved by mapping to Hermitian cases by using this Hamiltonian. So let's say H of K is non-Hermitian Hamiltonian, and we consider this extended Hamiltonian H tilde defined by this H and H dagger. Then you can see this Hamiltonian is Hermit. Okay. So then the question is the classification of this Hamiltonian. It requires the classification of this Hermitian Hamiltonian, and this problem is already solved by this step. Okay. This is a remark. So if there's a point gap with respect to reference energy 0, then this Hermitian Hamiltonian has also a finite energy gap with respect to energy, because the eigenvalue of this H tilde is the same as the singular value of H. Yeah, and as I said, classifying so the classification of non-Hermitian Hamiltonian is just that Hermitian H tilde, which is so in this sense, the classification problem is already solved.
Yeah, I think Tauta is trying to say there's a typo. Not
typo?
No. The point gap of H, not H.
Yes, sorry. Thank you.
And what's the meaning of H0? path.
This one?
Yeah, it's HK.
Sorry, this is also typo.
HK, right?
Yeah, this should be HK. Sorry. Sorry for many typos. Sorry. This should be HK, and this is H0, and this should be H pi. Sorry.
Okay.
Thank you.
My question is about, you try to connect the Hermitian to non-Hermitian system, right? So point gap is well defined in the non-Hermitian system, but how about line gap? Can you?
I explain.
Okay.
Okay, so yeah. Okay, so in this sense, proportional classification will point gap with respect to point gap is so. Okay, so how about the line gap? And here I consider real or imaginary line. And the real or imaginary line gap, then it can be Hermit or Pratik for keeping the real or imaginary line. This is the dictionary. This is done by. Okay, so this is a linear. So suppose I have real line gap here, and this blue region are eigenvalues. Okay, so this Hamiltonian has real line gap. So by using linear interpretation to -1 to 1, we get flattening Hamiltonian by this way. In this way. So the question is, the flattening Hamiltonian is Hermit one, but actually this can be done. So let me show. Yeah. So okay. So let me explain why this is true, why this can be done. So the first flattening can be achieved by introducing the projector. The projector is defined by counter integral with respect to the circle surrounding the energy, whose real value, whose real part is positive. Okay, in this way. So you can see, you can find that, you can check that this is really projector in the sense that its square is go back to itself. Okay. But not that this is not an element. But by using this projector, we can explicitly implement this linear interpolation. Okay. Then eventually we get flattening Hamiltonian. Like this. The next step is Hermitianization. Yeah, by using this decomposition, the Hermitian part and anti-Hermitian part, then we find that from the because this is a flattening Hamiltonian, H1 and H2 satisfy this relation, and introducing homotopy, we can see that homotopy from H1, large H1 to small H1, which is Hermit, then we can see its square is positive degree. That means that this Hamiltonian has real rank. Okay. Then the resulting Hamiltonian is Hermit H1, but this is not flat. However, we take the flattening to small H1 again to get the Hermitian and flattening Hamiltonian. Okay. So eventually, so what I said is that if the non-Hermitian Hamiltonian has real line gap, well, with keeping real line gap, this Hamiltonian can be Hermit and also flat. Okay. Then in the situation is the same as the point gap test. So the problem is just as a Hermitian problem, and in this sense, the classification problem is solve. Okay. Okay, so then the question is how to get the classification table. This one. Yeah. So I'm not sure this is so this is it's a completely Hermitian problem. So I'm not sure it. So I mean it's not a non-Hermitian problem. It's just a Hermitian problem. So yeah, but anyway, let me explain some best strategy. Yeah. Yes, because result in the Hamiltonian is Hermitian. Okay, so let me quickly explain how to get the classification table in Hermitian test. So as I said, for both point and line gaps, the classification problem is because of the Hermitian system, which is very established. So yeah, I use the classification Hermitian for cases. So strategy is the following. So first we classify zero-dimensional Hamiltonian, okay, and extend this result to finite space dimension. Okay. And I already introduced the Algorand-Silver symmetry classes. In the Hermitian test, we have 10 distinct fundamental internal symmetry for each block of reduced representation. It is called Algorand-Silver symmetry classes. Okay. So it is there are 3 types of symmetry: tensor symmetry and particle symmetry. There are anti-unitary, and also I have chiral symmetry. It is anti-commutative Hamiltonian. And because tensor symmetry and particle symmetry are anti-unitary, its square is either 1 or -1. Okay. As a result, we get this 10 distinct symmetry classes. Okay. And this 0 means that the absence of symmetry, and this 1 and -1 means that the tensor square. And here in this form, the sign is just a particle hole symmetry square. And here, 0, in this form, 0 means absence of chiral symmetry, and 1 means the presence of chiral symmetry. Okay. Okay, so yeah, we start with the classification of zero-dimensional Hamiltonian. It's just a Hermitian matrix, which is productive, and also with 10 Algorand symmetry constraint. The question is, what is the space of such matrix? Okay. The key technology, technical point is we introduced a kind of stable equivalence condition such that space becomes a classifying space. So let me explain what is a space of matrix. So I already yes.
I'm lost. Why do you need a condition S squared?
It is the same as productive. Productive is.
I think that is restriction beyond
Yeah, I see. Absolutely.
There are other reasons that for the eigenvalues.
Yes, yeah. Okay, so this is an example of the space of a matrix, Hermitian matrix, that I already discussed in the previous lecture. But let me repeat some point. So, okay, so 2 by 2 Hermitian matrix can be expanded as this way. Here, d0, dx, dy, dz are for real, and sigma is the Pauli matrix. So its eigenvalue is d0 plus minus the absolute value of matrix D. Then the flattening condition implies that we have either of the following 3 patterns. The first pattern is d0 is 1, and vector d is 0. And second pattern is d0 is minus 1, and vector d is 0. And third pattern is most interesting. d0 is 0, and vector d, absolute value of vector d is 1. Okay, then we find that the space of this Hamiltonian, whose square identity is given by the intersection union of 3 parts. The first one is this point, the second one is here, and third one is this point. Okay, so we generalize this kind of logic to any sizes of matrix. Okay, so this is a
Why D0 has to be integer?
D0 is integer.
Why is that so?
And your question is why D0 is integer?
I thought the eigenvalue of H is equal to D0 plus the magnitude of D back.
Yes, so but
You only require that to be plus or minus 1.
yes, I require the spectrum is either 1 or minus 1.
Plus 1/2. D0, why D0 cannot be 1/2?
1/2.
1/2 plus 1/2 is also equal to 1.
No, in that case, yeah, so you have zero eigenvalue. You mean 1/2 and 1/2? In that case, you have 0 eigenvalue.
Have an additional condition that H squared.
Yeah, X squared is identity. So is this constraint? Yeah. Okay. So yeah, let me super briefly introduce what stable equivalence is. So practically, the homotopy classification of Hamiltonian whose number space is finite at a fixed dimension by this setup in this setup 2 by 2 is not realistic. I mean, it is very difficult to mathematical problem to solve. For example, let's consider this is an example. Let's consider class A, I mean no symmetry, Hamiltonian, a 2 by 2 Hamiltonian in 3 special dimensions. Then the mathematically the classification is given by the equivalence, the set of equivalence club of classes of continuous map from 3-dimensional torus to 2 torus. Okay. Then the answer is the first you have to specify Chern numbers. There you have 3 Chern numbers, nx, ny, and z. And depending on this Chern number, in addition to Chern numbers, you can define Hopf invariant. But this Hopf invariant takes value in g sub 2 times range count divisor of the x and y and z. Very complicated. So you can see this is not group. Yeah. So yeah, but anyway, so it's super complicated. So it is not realistic to solve. So we want to find a good weak equivalence relation so that the mathematical problem can be solved. So this is called stable equivalence relation. Is introduced by Kitae. In this paper. So the point is that 2 Hamiltonian H0 and H1 are said to stable equivalent if there is some additional if there is additional Hamiltonian H prime, then H1 plus H prime and H0 and H prime and H1 and H prime are homotopically equivalent. Okay. This is yes, the notion of stably equivalent. Yeah, mathematically, yeah, there's some additional constraint, but yeah, essentially, yeah, stable equivalence is sufficient to understand the following process. So okay, so but this is mathematically motivated, but there's a physical motivation. The stable equivalence corresponds to the system which is stable against hybridization with higher or low energy bands, or the band folding by breaking transition symmetry by, for example, anti-ferromagnetic magnetic order. And as I said, the mathematical motivation is relatively easy to compute. Okay, so yeah, with this stable equivalence condition, let's reconsider the classification problem. So we consider what is the space of n by n Hermitian matrix whose square is 1. Okay, so this is just a repeat of the division Grassmann manifold. So it is diagonalized by unitary matrix U, and because this U is not unique, and also we have a n can be arbitrary integer from 0 to n. Okay. Then the H is eventually characterized by the union of Grassmann manifold like this. And by using stable equivalence, eventually the Hamiltonian is characterized by the so-called corresponding space. It's essentially the union, but this large n can be infinite. Okay. In this, so yeah, compared to this space of matrix with fixed size of Hamiltonian, this corresponding space C0 has a very useful property in mathematics. Okay, so this is an example of corresponding space. Let me show another example of corresponding space. Let's consider Hermitian matrix 2 by 2 n by 2 n Hermitian matrix whose square is 1 and also has parallel symmetry. I mean, the Hamiltonian is anti-commutative with some unitary matrix whose square is 1 and pressless. Then, without those of generality, we can say U gamma is sigma z polymetric. Then you can see that Hamiltonian H takes a form. Hamiltonian H has no diagonal element, and it is only characterized by off-diagonal element, and also this Q off-diagonal matrix takes values in unitary matrix. So that means this Hamiltonian is eventually characterized by unitary UN. Okay. And by using stable equivalence, eventually the Hamiltonian is characterized by this C1, corresponding space C1 is a kind of limit of unitary. Okay. Okay, so this kind of game we compute for all symmetry class. So, for example, this is class A1. So, yeah, with time partial symmetry, whose square is 1, we get this symmetry corresponding space. And also, this is corresponding space R1, and sorry, this is a symmetry symmetry class BD1. So yeah, you can see you can drive the corresponding spaces essentially orthogonal group, and for class D you can get corresponding space, this corresponding space, the orthogonal group quotient by emitter. Okay. If you are interested in the whole proof, you can check the slide. Okay. So I skip.
And after a quick question.
Yes.
You mentioned at some point that the fork edge correspondence is broken. So if we classify, but like why it is useful for us to classify the Hamiltonian of the fork if the fork edge correspondence is broken?
Boundary correspondence is broken.
I mean, in a non-Hermitian system, right? The Hamiltonian that we are classifying is basically the fork Hamiltonian of a non-Hermitian Hamiltonian, right? And if fork edge correspondence is not there, then yes, we can classify it, but what's the physical meaning that it can, or like a physical implication that we can get from this classification scheme, or like the result?
So you mean in reality we have to. So there's no you mean because there's no boundary correspondence between PBC Hamiltonian and the boundary.
Yes.
Yeah, I'm not sure. So my first point is I'm not sure there's a the boundary, the classification of open boundary non-Hermitian system is the same as the periodic boundary non-Hermitian system. This is but I think it's quite similar. So in this sense, yeah, it's meaningful. Yeah, so quantitatively, there's distinction because of context given, but classification probably very similar. So, yeah. Yeah, and also the skin effect is the existence of skin effect can be understood as PVC spectrum. Yeah, so this is obviously one application.
I see.
Of the classification of non-Hermitian system. Yeah. Okay, so so this is technical detail. Okay, and eventually I get more classifying space, and this is the table of classifying space and the topological classification of phi zero. It means counting disconnected part. Here, Z comes from the difference between comes from the number of occupied states, essentially. And it comes from orthogonal matrix. Oh. Because orthogonal matrix you can get plus minus sign from determinant. Okay, so then we got classification for zero-dimensional system. So the question is how to generalize this classification to finite space dimension. So let me explain a strategy. So some still stable equivalence again, the topological structure from different origin can be discussed independently. So for example, mathematically in these spatial dimensions, block momentum space is of course a d-dimensional torus. So it's complicated. However, with stable equivalence, the topological classification is decomposed into subspheres. Is to P, where P is spans from 0 to T. It is like the origin of topological invariant can be decomposed to the independent, like the Hamiltonian has the Skamian structure and vortex structure. You mean the Skamian structure? Skamian property is from two-dimensional property, two dimension, and vortex property is from one dimension. But with stable equivalence, we can decompose these complicated interplay to the independent Hamiltonians. That means we can assume the broken momentum of space is just a D sphere, not torus. Okay. Okay, so the second technology is we can assume the form of Hamiltonian by using case theory. So representative Hamiltonian to represent the classification classification rank G or G2 can be a form of Dirac Hamiltonian practice. So okay, so originally Hamiltonian HK is any Hamiltonian, but when in the context of case theory, it can be it can be the form of Dirac Hamiltonian. So yeah, K in linear term and the mass term. Where the point is, this gamma matrix which are anti-commutative with each other, and also this gamma is anti-commutative with mass term H. Okay, and the mass square is 1. Okay, then it is very then the classification problem becomes very easy. Because adding the spatial dimension is the same as adding the gamma matrix. Okay, and adding the gamma matrices is the same as adding the chiral symmetries. Okay, then the problem is we solve what happens if we add chiral symmetries in the constraint of the mass matrix. Okay, so then it is this kind of technique is known as dimensional isomorphism in the case theory. So actually, adding spatial dimension is the same as the shift of symmetry classes. Okay, AHBA and A1 derivatives. The key observation is that two chiral symmetry can be solved trivially. So suppose we have two chiral symmetry for matrix M, and sigma x is anti-commutative with M, and sigma y is also anti-commutative M. Then the space over sigma space, the Pauli matrix, the space of Pauli matrix, the form of M, matrix M is fixed. I mean sigma z. Okay, to preserve this symmetry. Then this remaining matrix M tilde has no symmetry. So this is the origin of simplification of problem. Okay. Yeah, I think it's already technical details, so let me skip. So if you are interested in the detail, you can check the slide. So okay, so eventually I get yeah. So this the shift of symmetry classes. Okay, and without here dimensional symmetry and hypersymmetry, this shift is twofold, has a twofold periodicity. And with time class or hypersymmetry, this shift is found to have eightfold periodicity. It's called both periodicity in the case theory. So the eventually topological classification D-dimensional Hamiltonian with alternative symmetry class is given by this phi 0 of classifying space. Then I get this then I got this symmetry, this classification term of Hermitian physics. Okay. Okay, so then the classification problem is already solved. So the remaining task is to identify how 38 non-Hermitian symmetry classes are mapped to tenfold Lagrange singular symmetry classes in Hermitian systems. So yeah, this is very easy. So let me explain why it is So for point gap topological phases, we consider Hermitianized double Hamiltonian H children. Then you can see this Hamiltonian H children has additional parallel symmetry by sigma z, okay, by this construction. So in other words, non-Hermitian symmetry for H is mapped to, sorry, the symmetry in non-Hermitian system for H is mapped to symmetry for Hermitian system represented by H children with this additional parallel symmetry. Okay? Then we can check. Then we can identify what is the exact what is the symmetry here in the Hermitian system. Okay. Okay. So for real and imaginary line gap, we have our as I said, non-Hermitian Hamiltonian can be element or anti-element depending on the line gap, the type of line gap. Then in the view of this double Hermitian double Hamiltonian, the Hermiticity of H, Hamiltonian H, is the same as additional parallel symmetry for double Hamiltonian H children. Okay, for Hermitian for element test, Hermitian test, this is the same as imposing additional parallel symmetry by sigma y. Okay. For imaginary line gap case, it can be anti-element, and this is the same as imposing. Then we can identify symmetry group, and this is algebraic relation for Hermitianized the Hermitian case. Okay.
So the classification for any dimension is the same.
Topological classification, no. Yeah. Okay, so then eventually after identifying the map of the symmetry plus in Hermitian system, we get this kind of symmetry classification table for non-Hermitian topological phase for each symmetry classes. In this slide, I just showed 8 symmetry class, but there are other 30 symmetry classes. Okay, here P means point gap, and R and Li represent real line gap and imaginary line gap respectively. Okay, so here if you are interested in this picture, you can see here. Okay. Okay, so in last 5 minutes, let me introduce the notion of intrinsic non-Hermitian topology. Okay, so this is this is the same table of same classification table of non-Hermitian system. So let me focus on class D. One special dimension. Then with line gap, as I said, line gap is the same as non-Hermitian physics. And class D is a particle symmetry, so we have edge 9 and 0. Okay. But for point gap, we have G2 again. What is the meaning of this G2? Actually, this is the same as the Hermitian case. So because the class D particle symmetry is a constraint on the spectrum as follows. I mean, E is mapped to minus E. Then the zero energy is special. I mean, it's a zero energy is protected by this type of particle symmetry. So that means binary zero mode is robust, and even if there are no Hermitian perturbation exists. Actually, we find that non-Hermitian G2, non-Hermitian G2 classification is characterized by non-Hermitian, this kind of non-Hermitian G2 invariant. Okay. And we find that this invariant corresponds to the existence minor 0. Okay, so then the question is this unique to non-Hermitian systems or not? So I mean, so this table has, in some sense, lack information. I mean, which classification is specific to non-Hermitian system or not? So yeah, so yes. So the question is there any good approach to extracting topological phase realized only in non-Hermitian system? Our proposal is that we take the co-kernel of the homomorphism from line gap topological phases to the point gap topological phases. Okay, so because this homomorphism exists because line gap implies point gap. Yeah, it is obviously true. So if the spectrum has line gap, this spectrum has also point gap, right? But opposite direction is not true. But yeah, this direction is true. Okay. So that implies if we have some topological phases in with respect to line gap, then this is well defined even for point gap topological phase. Even as a point gap topological phase. So that means we have the map from real line topological phases to point gap topological phases, and also imaginary line gap topological phases to point gap topological phases. Okay. Okay, so the meaning of this homomorphism is that the image of these homomorphisms FR and FY can be realized as a Hermitian system. Okay. So in this sense, it is not intrinsic to non-Hermitian system. But so we come up with a good mathematical object. The quotient of point gap topological phases over image FR plus image FY, I mean the image of line gap topological phases. So this can be calculated very easily by using the similar technique, case theory. And this is the result. So for outrun supersymmetry classes in non-Hermitian system, this is the classification of table of intrinsic non-Hermitian topological phases. For example, here I have Z, and this corresponds to non-Hermitian skin effect. And here I have Z, this corresponds to the kind of generalization of non-Hermitian skin effect in 3-dimensional. So it is physically it is induced, the skin effect induced by magnetic space. Okay. And this is AZ dagger class. And yeah, A2 dagger, I will have a G2 classification, and that means actually it is found that this corresponds to the kind of G2 generalization of non-Hermitian skin effect. Okay, and this is AZ symmetry with additional sublattice or pseudo hermiticity. Okay, and a few examples is this. I think a few examples was discussed in the literature. For example, D for in this two spatial dimension with SP plus S minus the kind of sublattice symmetry. This D2 is partially D2, and oh yeah, this example is discussed about this paper. And oh yeah, eventually I have for the classification. But yeah, this is a remark. I'm not familiar with recent development, so I'm not sure how many which symmetry groups are studied seriously. So yeah, reference-based is not very limited because of the lack of minorities current reference. Okay, so this is an example of S3 plus some non-trivial example, but we need to skip because I have to. Okay, so this is summary. So in this lecture, I gave a introduction of the notion of one particular non-Hermitian systems, and I explained some basic phenomena in non-Hermitian systems, one the expression point, non-Hermitian scheme effect. And to define the topology of non-Hermitian system, we have to define firstly point gap and line gap conditions. And also, I explained different symmetry classes in non-Hermitian systems, and explain briefly topological classification, and not all over topological classification in point gap system is super interesting, as I explained. Yeah, but we have to extract very interesting non-Hermitian topological pages by using map between line gap topological page to point gap topological page. As a result, we get the classification table of introducing non-Hermitian topology. Okay, yeah, that's all. Thanks for listening.
Questions?
Yes.
So, the classification scheme, like the restriction on the Hamiltonian, you actually do not need the demonstration symmetry. Right?
Yeah, right. Yeah, we expect, but I expect, but yeah, I think the ongoing study. I think it's
ongoing study.
Ongoing, I think.
Following the logic, it seems like translation symmetry is not really important. But when you generalize it to higher dimension, it will be important.
You mean the absence of translation symmetry?
Yeah.
Generalized.
Yeah, when you generalize it to the higher dimensional case, I guess it is also not important, right?
Yeah, not problem, but I don't know how to study.
I see.
But coarse geometry, yeah, can deal with this situation.
Okay.
Yes.
Yeah, I have a very naive question. Can you go to page 76 of the first classification? Yeah. So I don't understand how this is constructed. I was expecting to see something more simple, like just a copy of the temporal wave appearing here. But then here you see more complicated structure and graphs, so on.
So yeah. So if we focus only on point gap, instead you can see the same table. G2 G2 0 2Z 0 0 0 Z. In zero dimension, and in one dimension, Z G2 G2 0 G2 Z 0 0 0. Okay, so this is just copy. And also in the line gap, near line gap, you can find that this is also copy. So yeah, this is so yeah. So for each point gap, for each gap condition, you can find.
Is the dimension the same or?
Dimension same? No.
If I just focus on zero dimension and do T, I see use this outcome same classification as the.
No. Dimension is 60 by 1 plus 2. Yeah. Because of the additional piracy in the Hermitian system. I mean, that because of additional chiral symmetry of double the Hermitianized Hamiltonian. Yeah.
This imaginary line, yeah. Yes. Where this Z2, and then this one Z2 plus Z2.
Yes, so sometimes we so as I said imagine running up with the same additional two chiral symmetries. Yeah, and sometimes this additional chiral symmetry combined with original symmetry that we want, we get G to unitary symmetry. Then the Hamiltonian is block diagonalized. Then we get sometimes D2 plus D2.
That depends on the class.
Yeah, depends. One general generic feature is because all classification is because of zero-dimensional KCLT. Then the classification is either 0 or Z or Z2, or it is direct sum. There's no Z because of G in this algorithm.
That's a naive question. So you're basically classifying the Hamiltonian, but for a quantum system, I think we, to some extent, like we want to classify wave function, which transform project beyond the symmetry. So how to bridge these two?
Yeah, I want to know that.
Not yet, no.
I want to know. I'm not sure. So
it's open yet right now.
Partially I solved this. So I think your question is the same as how to define the topological invariant from wave function.
Yes.
Yeah.
Is it equivalent to this thing or maybe not?
Yeah, I think partially, yeah, it's solved. And yeah, I don't know the complete answer.
Okay.